Hello, grade 11 chemistry class. Welcome to our first video lesson on chemistry. And today we're going to start with the mole. And you've probably heard of moles before. Moles are cute little animals like this guy right here. And he has, if you look at his anatomy, he has a very tiny ear, a tiny dark eye, pointed snout, perfect for burrowing through the ground. And then he's got these shovel-shaped thick clawed feet. They're good for clawing through the ground as well, and then lots of fur on his body and stuff. Anyway, we don't want to get too distracted by our picture of the mole here. What we're really here to talk about is grouping of quantities. And you've probably grouped quantities before. For example, you've talked about eggs, or you've gone to the store to buy eggs, and eggs are typically sold by the dozen. So you can get a dozen eggs, and what that really means is that you're getting 12 eggs in total. So that was a grouping of eggs. If you go to Tim Hortons on your way to school or on your way home, you may be getting a half dozen donuts when you stop in, enough for the family for dinner or for dessert. And what that would just mean is you're getting 6 donuts. When you leave for school in the morning, you may be putting on a pair of shoes. I'm sure you would be. And what that basically means is that you have 2 shoes. We've got all kinds of ways of grouping things. And it generally makes our life a little bit easier just to have these groupings. For example, we know to order 2 dozen eggs to last us the weekend. And when we do that, we know that we're going to be getting 2 times 12 per dozen. So in total, we're going to be getting 24 eggs. Right? Or if we go to a bakery and we order 3 dozen donuts, just enough to provide enough donuts for a class, perhaps, then we're going to be getting 3 dozen times 12 in a dozen. We'll be getting 36 donuts. 36 donuts. Okay, or if we go to a shoe shop and we need 3 pairs of shoes, one for running around with, 1 pair for dress, and another for something else, maybe dancing, then we're going to be getting 3 pairs of shoes times 2 shoes per pair, and that equals a total of 6 shoes. Okay, so and then we've got other things like kilometers. Kilometers, if we wanted to put kilometers into the base unit meters, then we might multiply 4 kilometers times, and it's 1,000 meters per kilometer, and that would give us 4,000 meters, right? Okay, we've got all kinds of ways of grouping numbers. So there you have it. A mole is a measure of the number of tiny particles of a particular substance. So you can have 1 mole of a bunch of different things. You can have a mole of nitrogen molecules. And what that would mean is that you've got 6.02 times 10 to the 23, a very large number of molecules. Okay, and you can see the convenience of using the mole, just so you don't have to use scientific notation all the time to represent numbers of particles. Carbon atoms, even though we're not talking about molecules, we're talking about atoms, we can still use the mole. If we say 6.02 times 10 to the 23 atoms, we're basically talking about 1 mole of carbon atoms. Okay, even an ionic compound like magnesium nitride. Okay, if we're dealing with compound units, because ionic compounds are referred to as compound units, not molecules, 6.02 times 10 to the 23 compound units would basically represent 1 mole of magnesium nitride. Okay, and 6.02 times 10 to 23, what that is actually, it's a shortened version of the real number for Avogadro's constant, which you can see here, 6.02214179 times 10 to the 23. We'll never actually use that kind of precision as we're using Avogadro's constant, but So all you really need to pay attention to is 6.02 times 10 to the 23. But there you have it, Avogadro's constant. We're going to be using it a lot. So it was made up by Italian physicist Amedeo Avogadro. And so we'll use his constant now as we're converting between number of moles and number of particles. So if we're going from number of particles to number of moles this way, then we're going to be dividing by Avogadro's constant. If we've got an amount of material in moles, then we're going to be going this way. We're going to be multiplying by Avogadro's constant in order to get to the number of particles. If you're not sure what I'm talking about exactly, let's take a look at this example here. So we've got 4 moles of methane which are combusted in a flame. How many methane molecules were consumed in the reaction? So in order to calculate that, we've got moles. We need to get to number of molecules here. So I'm going to take, okay, so I'm gonna represent the number of molecules with the big N there. N of CH4 is equal to number of moles, N of CH4, okay, times, because we're going towards particles, so multiplied by Avogadro's constant, so 6.02 times 10 to the 23. Plug in the numbers. Number of particles of methane is going to be equal to 4 moles of CH4 times Avogadro's constant. Okay, if we work that out on a calculator, we're left with 2.408 times 10 to 24. Okay, so that's what we're dealing with. 4 moles of methane is exactly this many molecules of methane. Okay, they're equivalent. Going the other direction, okay, so if we have a number of particles and we want to go to number of moles, here's another example. So a chemical reaction yielded 3.03 times 10 to the 23 molecules of carbon dioxide gas. How many moles of the gas are there? Or what is the amount? Basically, the word amount is used to describe how many moles. Okay, what is the amount of carbon dioxide that was yielded? So in this case, we're trying to find the amount. The amount is represented, the symbol is small n, and we're dealing with carbon dioxide gas. Okay, so the amount of carbon dioxide is going to be equal to number of particles, okay, divided by Avogadro's number, 6.02 times 10 to the 23. Okay, 6.02 times 10 to the 23 particles per mole, basically, is what we're dealing with. And so we've got, if we were to plug in the numbers here, we've got 3.03 times 10 to the 23 molecules divided by Avogadro's number. Okay, here are tens. We're going to cancel with each other because they're raised to the same exponent. So it's basically just 3.03 times, or divided by 6.02. Okay, and that works out to be 0.503 moles. Okay. So 3.03 times 10 to the 23 molecules of carbon dioxide is equivalent to 0.503 moles of carbon dioxide. That's the amount of carbon dioxide right there. Okay. A bit of a different example.